In section 15.2 of Stewart, we learn how to integrate a function of two variables over regions of type 1 and regions of type 2. So we're no longer restricted to doing integrals over a rectangle. Now we can handle these more general types of regions. A type 1 region looks like this. Here we have the graph. This lower curve is the graph of G1. This upper curve is the graph of G2. Here's A, here's B. And this region D consists of all points x, y in the plane such that x is between A and B and y is between G1 of x and G2 of x. So here's our region D that we're going to integrate over. And in section 15.2, we learned this formula. This integral over D is equal to the integral from A to B of the integral from G1 of x to G2 of x of f of xy dy dx. This is the formula that we use to evaluate integrals like this. That's a type 1 region. And a type 2 region looks like this. Here, this curve on the left is the equation of that curve is x equals h1 of y. The equation of this curve on the right is x equals h2 of y. Here's C, here's D. This region D consists of all points x, y in the plane such that y is between C and D and x is between h1 of y and h2 of y. So here's our region D. And we want to do an integral of a function f of two variables over the region D. And in section 15.2, we learned this formula. We learned how to take this integral and write it as an iterated integral like this. The outer integral is with respect to y because y goes from C to D. And the inner integral is with respect to x because for a given value of y, x goes from here over to here. X goes from h1 of y to h2 of y. So the inner integral is with respect to x. This is the formula that we use to evaluate integrals like this over a type 2 region. So here's an example. We want to integrate this function over the region D, where D is the region bounded by these two parabolas. So let's draw a picture of this region. Y equals 2x squared is a parabola that looks like this. And y equals 1 plus x squared is a parabola that looks like this. And so this shaded region, that's the region D that we want to integrate over. And let's find the coordinates of these 2 points where these two curves intersect. So at these points of intersection, we have 2x squared equals 1 plus x squared. So that means that x squared is equal to 1. So x is equal to plus or minus 1. And so here's x equals 1. And here is x equals minus 1. And if x is equal to 1, the corresponding value of y is y equals 2. So, okay, we have drawn a picture of the region D. And now this is a region of type 1 because D can be written as the set of all points x, y such that x is between minus 1 and 1 and 2x squared is less than or equal to y, which is less than or equal to 1 plus x squared. This region D is a type 1 region. It has this form. Okay, so the integral over d of x plus 2y dA is equal to, let's just use our formula for a type 1 region, the integral from -1 to 1 of the integral from 2x squared to 1 plus x squared, and then we're integrating x plus 2y. The inner integral is with respect to y. The outer integral is with respect to x. This is the integral that we have to evaluate. So let's work on evaluating this inner integral. We need an antiderivative of this function with respect to y. And here's an antiderivative of this function with respect to y. It's xy plus y squared. And now we take our antiderivative and we evaluate it at the endpoints. So from here to here, we evaluate it from 2x squared to 1 plus x squared. And when we plug in 1 plus x squared for y, we get x times 1 plus x squared plus 1 plus x squared squared. And when we plug in 2x squared for y, we get x times 2x squared plus 2x squared squared. Now let's just expand and simplify. So this is equal to x plus x cubed plus, and let's expand this, 1 plus 2x squared plus x to the 4th. And now let's distribute this minus sign. So we have minus 2x cubed minus 4 times x to the 4th. Okay. So here we have minus 4x to the 4th plus x to the 4th. So that gives us a minus 3x to the 4th. We combine those two terms. Here we have minus 2x cubed plus x cubed. That gives us a minus x cubed. So we've used those two terms. And then we have a plus 2x squared plus x plus 1. That's what the inner integral reduces to. And so now we have to do the integral from -1 to 1 of this function. We have to do the integral from -1 to 1 of this function. Minus 3x to the 4th minus x cubed plus 2x squared plus x plus 1 dx. And let's find an antiderivative of the function that we're integrating. So here an antiderivative is minus 3x to the 5th over 5. Here an antiderivative is minus x to the 4th over 4. An antiderivative of this term is 2x cubed over 3. An antiderivative of x is just x squared over 2. And finally, an antiderivative of 1 is just x. We take our antiderivative and we evaluate it at the endpoints. And what we get is going to be minus 3/5 minus 1/4 plus 2/3 plus 1/2 plus 1 minus, now we plug in minus 1 for x, so that gives us 3 over 5 minus 1 over 4 minus 2 over 3 plus 1 over 2 minus 1. Okay, now this minus 1/4 is going to cancel out here, And this 1/2 is going to cancel out here. And what we're going to be left with is -6/5 plus 4/3 plus 2. And finding a common denominator, this is -18/15 plus 20/15 plus 30/15. So that is 32/15. That is our final answer. Okay. So that's an example of integrating a function over a region of type 1. Now let's do another example. In this example, we want to find the volume of a solid that lies under the surface z = x² + y² and above the region D in the xy plane that's bounded by this line, y = 2x, and this parabola, y = x². So let's first draw a picture of the region D. So y = x² is a parabola that looks like this. There's y = x², and y = 2x is a line that looks like that. So here's our region D shaded in right there. And let's find this point of intersection. At this point of intersection, we have 2x = x². So assuming x is non-zero, let's divide both sides by x, and we'll get 2 is equal to x. Okay, so here x is equal to 2. And this region D is a type 1 region because it can be expressed as the set of all points x, y such that x is between 0 and 2, and y is between the lower curve is x², and the upper curve is 2x. D can be expressed like this. This is how you express a type 1 region. So let's use our formula for integrating a function over a region of type 1. And what function do we want to integrate? Well, we're trying to find the volume under this surface. We're trying to find the volume under the graph of this function, x² + y². So the function that we are integrating is x² + y². And according to our formula for integrating over a type 1 region, this integral is equal to the integral from 0 to 2 of the integral from x² to 2x of x² + y². The inner integral is with respect to y. The outer integral is with respect to x. Okay. Now let's evaluate the inner integral. We need an antiderivative of this function with respect to y. So here we go, x² y plus y³/3. That's an antiderivative of this function with respect to y. We take our antiderivative and we evaluate it at the endpoints. So from x² up to 2x. When we plug in 2x for y, we get x² times 2x. When we plug in 2x for y³, we get 2x³ / 3. when we plug in x squared for y, we get x to the fourth plus x squared cubed over 3. Now let's simplify. So this is equal to 2 times x cubed plus 8 times x cubed over 3 minus x to the fourth minus x to the sixth over 3. This is what the inner integral reduces to, and we can combine these two terms here. So 2 plus 8 over 3 is equal to 6 over 3 plus 8 over 3, so that's 14 over 3. So what we have here, the inner integral reduces to 14 thirds x cubed minus x to the fourth minus x to the sixth over 3. That's the inside integral. Now we have to integrate this function. We have to integrate this function from 0 to 2. So let's do integral from 0 to 2 of 14 thirds x cubed minus x to the fourth minus x to the sixth over 3 dx. So to evaluate this integral, we have to find an antiderivative of this function. And an antiderivative of this function is 14 times x to the fourth over 12 minus x to the fifth over 5 minus x to the seventh over 21. And we evaluate our antiderivative from 0 to 2, but first let's simplify this first fraction. 14 over 12 is the same thing as 7 over 6. So we have 7 over 6 x to the fourth minus x to the fifth over 5 minus x to the seventh over 21. That's our antiderivative. We have to evaluate our antiderivative at the endpoints. So from 0 to 2, we're integrating from 0 to 2. Now when we plug in 2 for x, we get 7 over 6 times 2 to the fourth, which is 16, minus 2 to the fifth over 5, and 2 to the fifth is 32, minus 2 to the seventh over 21, so that's 128 over 21. And if you simplify this, you get 216 over 35. So that's our final answer. Example 3, let's compute the integral of this function over the region D, where y is between 0 and 3, and x is always between 0 and y. So first, let's draw a picture of D. Here's our xy axes. Y is always between 0 and 3. Here's the line y equals x, and x is always less than or equal to y and greater than or equal to 0. So that means that this shaded region is our region D that we're integrating over. Now this is a region of type 2, so let's use our formula for doing integrals over regions of type 2. According to that formula, the integral over D of e to the minus y squared dA is equal to the integral from 0 to 3 of the integral from 0 to y of e to the minus y squared dx dy. To evaluate this inner integral, we need an antiderivative of e to the minus y squared with antiderivative with respect to x. And here's an antiderivative, x e to the minus y squared. So let's take our antiderivative and evaluate it from 0 to y. When we plug in y for x, we get y times e to the minus y squared. When we plug in 0 for x, we just get 0. So this is what the inside integral is equal to. So we have to now do the integral from 0 to 3 of y times e to the minus y squared dy. Okay, so we need an antiderivative of the inside, and here's an antiderivative, minus 1/2 e to the minus y squared. Let's check that this antiderivative is correct. If we take the derivative of this thing with respect to y, and we have to use the chain rule, then we get e to the minus y squared multiplied by minus 2y, and there's cancellation with the minus 1/2, and we're left with positive y, which is perfect. Now, how do we think of this antiderivative? One way to do it, if you like, is to use substitution to come up with this antiderivative. Now we're going to take our antiderivative and evaluate it from 0 to 3. When we plug in 3 for y, we get minus 1/2 e to the minus 9. And when we plug in 0 for y, we get minus 1/2. So the final answer is 1/2 minus 1/2 times e to the minus 9. That's our final answer. Now it's interesting to look at what would have happened if we had taken the same region D, but instead of viewing it as a type 2 region, we could have viewed it as a type 1 region. And if you view this as a type 1 region, then that means that we're going to think of D like this. D is equal to the set of all points x, y, such that x is between 0 and 3, and y is between 3 and x. That's an equivalent and an equally correct description of D, and this way of looking at D shows that D is also a type 1 region. So let's try to do this integral using the type 1 formula. So according to the type 1 formula, the integral over D of e to the minus y squared dA is equal to the integral from 0 to 3 of the integral from x to 3 of e to the minus y squared dy dx. But now we have a major problem because there is no elementary antiderivative for this function e to the minus y squared. We cannot find an antiderivative of this function with respect to y. So when we do it this way, our approach actually fails because we can't do the integral. So that's an example where viewing the region as a type 2 region led to an integral that we were able to evaluate, whereas viewing the same region as a type 1 region led to an integral that we could not evaluate. That's an interesting thing that happens sometimes.